connections, bad fuses or breakers, and yet there is still an obvious anomaly. This problem is that of uneven phases. Since most industrial facilities use three-phase power, there will be three phases or legs going to machinery and equipment. A problem in the stator of a motor can cause one leg or phase to draw more or less current. In most applications, the phases should all have approximately the same load and therefore the same temperatures. One leg that is hot indicates uneven phases, and other tests should be performed to determine the actual source of the problem. Transformers are designed to operate at 100% capacity. Since most of them do operate at or near capacity, it is imperative that they are in good condition. Most transformers require some form of cooling due to the excessive heat they generate. The cooling is normally an oil bath that uses convection to carry heat to the cooling fins. The unit must not overheat or it may explode, sending contaminants into the environment. A common cause of overheating is the coolant oil may build up a sludge and clog some of the cooling fins. This example of a large transformer has some clogged fins, which is indicated by the cold or dark regions. A good cooling fin or tube should be warmer at the top and colder at the bottom. Other types of transformers can exhibit hot spots caused by internal breakdown of the transformer. Additional tests should be performed to confirm the level of degradation. Switch yards can be inspected from the ground, with the best result being achieved at night just after sundown. Hot spots are usually the focus, and the night cooling enhances this, making them much easier to locate. Components in a switch yard include switches, fused disconnects, transformers, capacitors, wire, bus or terminal bars, oil or gas circuit breakers, and reclosures. Remember that some hot spots may be naturally occurring in some equipment due to internally mounted strip heaters used to keep out moisture. Transformers and capacitor banks are naturally warm. On these, the presence of cold spots could indicate an anomaly. All wires should be at or near ambient temperature with no more than a 3 degrees centigrade rise. Wires warmer than that could indicate an undersized wire or an overload condition. Remember that here too, wires that have a barber pole striping or candy striping indicate some broken strands with the unbroken wires carrying the total load. In switch yards, the hot spots can be at such a distance that they may be difficult to detect, and a telescopic lens would be very helpful. View the hot area from other positions to pinpoint the source of the hot spot. Some mechanical problems can be clearly seen with a thermal image. When a bearing degrades or there is inadequate lubrication, the friction generates heat, which can show up as a hot area at the bearing housing or bearing mounting location. Remember that for most oil lubricated bearings, the oil breaks down at 160 degrees Fahrenheit. Bearings that are in this range are too hot. Misalignment is a fault that is easily recognizable using thermal imaging. The easiest place to spot misalignment is at the coupling. A series of tests was performed on a motor generator set using various couplings in alignment and 4 amounts of misalignment. Each setup was run for 4 hours and then thermal images were recorded. Both the aligned condition and misaligned condition are shown here for each coupling type. Notice how the aligned coupling remained cool, while the misaligned condition is clearly hotter. Depending on the coupling type, the difference between an aligned condition and a misaligned condition is as much as 65 degrees Fahrenheit. It should be noted that the amount of misalignment shown in these examples is very minor and definitely not considered gross misalignment. Belts are commonly used in most manufacturing facilities, but can generate excessive vibration when they are carried on eccentric or misaligned sheaves. Since belts rely on friction to work, they will generate some amount of heat. However, misaligned sheaves cause the belts to ride up on one side, causing more heat on that side of the V-groove. The thermal image will indicate this misaligned condition. The thermal image of a multiple belt drive will indicate some temperature variations among the belts due to differences in tension. Some manufacturing processes require specific and uniform temperatures in order to maintain high quality. Thermal imaging can provide the information needed to correct problems and increase quality production. This example shows the paper from a paper machine as it is being rolled up. It has just come from the dryer section where it should have dried uniformly, yet there is definite streaking indicating a cold area. This area did not dry thoroughly, which points to a problem with the drying process. This example is a coating process where the coating slides off a roll and coats the product. Tons of the product were rejected because the coating did not meet the requirements. The thermal image makes it clear that the coating does not maintain a uniform temperature as it is dispensed, and this caused the irregularities in the product. Many facilities have processes where heat is used for the process and must be contained. It could be a furnace for a boiler, an oven to cure or cook a product, a kiln, steam pipes, or some other hot area. Insulation panels on the walls must prevent the outside surface temperatures from exceeding limits as set forth by OSHA. Breakdown of the insulation or seals of the closures is easily detectable with thermal imaging. Open joints between the internal refractory panels are easily recognizable. Be sure to record accurate surface temperatures for reporting so precautions can be made to protect personnel. Storage tanks have their own set of peculiarities and sometimes present special challenges, one of which is determining the product level. If the tank is outdoors, survey it at night when the air cools the tank down to the product level. The contents will be warmer and indicate a definite thermal differential. If the survey must be performed in daylight hours, choose a sunny day when the sun heats up the tank surface, but the product does not absorb the heat quickly and will indicate a cooler temperature. Thermographers complain that it takes too long to compile the information and get a report back to the customer. Customers complain about a 3 or 4 week turnaround time. A good system documents the essentials and takes the headache out of the paperwork. The notes are already electronically recorded in the field, which will spare many hours trying to sort notes, find notes, or recall information. The information is downloaded to the computer into CSI's infra-analysis software, where a database of records and images are kept for each machine. The database stores the machine or equipment name and description, the fault location, the surveyor's name, and temperature information including the exception temperature, the reference temperature, the background temperature, ambient temperature, the delta temperature, and the full load delta temperature. Electrical parameters can also be recorded for the phase leg or circuit number, the voltage, the actual load in amps, the rated full load, and the percentage of the full load. Based on your findings, you must recommend a course of action for correcting the anomalies. These can be stored in an area for recommended actions. All of this documents your work, but the customer wants to see the picture or thermal image, and in color. Individual frames of the video footage are digitized and stored on the computer where we can retrieve and view them. The pictures can then be printed as part of the report. The report can also be put into a slideshow on a disc and given to the customer. The customer simply views the visible and thermal images at his convenience, and since all the information and recommendations are included, you have a happy customer. And that's all in a day's work. Let's take a look at some special considerations you'll need to know when performing thermography surveys. Earlier in the program, we showed you examples of performing outdoor surveys. These require special consideration due to the sun's heat and wind, which can be used to benefit you, but if not understood, can lead to wrong conclusions. The sun radiates heat to objects or surfaces, which will either absorb or reflect the heat. The heat absorption is called solar gain or solar loading. This is evident at night when viewing an object like a telephone pole. It should be the same temperature on all sides. However, it absorbed energy where the sun rays hit it, and now it is releasing or radiating that heat back to atmosphere. This causes the pole to appear striped. This solar loading can be used to your benefit in some applications like roof surveys, where you are looking for wet insulation. The dry roof radiates its solar gain much faster than the wet areas, causing the wet areas to appear much warmer. Solar reflections are just that, reflection of the sun or atmosphere. A reflective surface, or one of a low emissivity value, will cause you to actually measure the sun or whatever it is reflecting. At night, the reflective surface will appear much colder since it is reflecting the cold atmosphere. When you are scanning during daylight or dark, if you can visibly see a bright spot or reflection, then the same shape will be in the thermal image. In the sunlight, it may be difficult to determine whether the spot is a reflection. The reflective temperature could mask an anomaly. For this reason, most outdoor scanning is performed at night. The wind is another consideration that affects your temperature readings. Wind can blow the heat waves away and cause an object to appear much cooler. When scanning the exterior of a building for heat loss, wind will affect your measurements. When solar gain, reflection, or wind are present, be sure to note it well enough that another person could perform the scan and achieve the same results. Earlier in this program, in our discussion on emissivity, we mentioned that gray bodies need to be compensated for to bring their values up to 1 in order to achieve an accurate temperature measurement. For example, if the actual temperature of an object is 100 degrees and its emissivity is 1, the thermal image will indicate 100 degrees. If the emissivity is 0.95, then it would display 95 degrees. If the emissivity is 0.4, it would indicate a temperature of 40 degrees. We would need to compensate for the poor emissivity, so the indicated temperature would be the actual temperature. The camera allows us to plug in a value for the emissivity. Then it will make the correction and display the actual temperature. There are 3 ways to determine the emissivity. One is to use the tables provided by the manufacturer. These tables are really estimations and the least accurate of the 3 methods. The second is to use a black body as a reference, and the third is to use a known temperature for comparison. Either of the last 2 will provide accurate results. Plug in the numbers and the temperatures will be accurate. Earlier we showed you that infrared energy is in the range of 2 microns to 1,000 microns. The infrared cameras are not sensitive to the area above 14 microns. And the first 14 microns are divided so that one group is referred to as long wave and the other as short wave. Actually, the short waves are considered to be in the range of 2 microns to 5.6 microns. The long waves are from 8 microns to 14 microns. This leaves an obvious gap from 5.6 to 8 microns. This region is not used because energy here is absorbed by the atmosphere and is not available to us. The camera that is sensitive to the shortwave region is better for high temperatures and is not as susceptible to night sky reflections. This means it would be best for surveying roofs of buildings and any high temperature processes that use refractory ovens or hot chemical processes. The long-wave cameras are best for ambient temperatures and less sensitive to solar reflection. They would be best for performing daytime scans of switch yards or electrical applications that are not subject to extreme heat. Use the wavelength that is best for your application. We have provided an historical background and highlighted some of the common uses and characteristics of the infrared thermographic imaging. Whether troubleshooting or performing routine PDM surveys, you'll find many more applications for this growing technology. Thank you for joining the thousands who have selected CSI training for PDM and RBM application training. We are confident that the application tips and techniques presented here will help you in your infrared thermography analysis. We look forward to assisting you achieve success in your future endeavors.